Hello and welcome to this 17th session of Symmetry in Chemistry. So we're going to look at linear molecules today and their character tables, which actually chemists often don't really think about very much. And we're going to go on to start looking at the dioxygen molecule, O2, which is really a uniquely interesting molecule, and we'll go on to look at that in some more detail next time. But starting off with these character tables, so we've got two character tables for linear molecules, C infinity V and D infinity H. So C infinity V, this is the smaller character table, and we use this for the heteronuclear diatomics. That's to say where the two ends of the molecule are different from each other. And so in this case we're going to lack the centre of inversion symmetry and those perpendicular C2 axes. So things like carbon monoxide, so we'll be looking at that molecule a bit later on. But we're going to be mainly focusing on D infinity H because we're going to be looking at homonuclear diatomics to begin with, especially oxygen. And so with this centre of inversion symmetry, it's effectively, it's doubling the number of symmetry operations effectively, because it gives us all of these improper rotations as well, because we've got this perpendicular mirror plane perpendicular to the principal axis, and it also brings in the infinite number of C2 rotations. And so looking at the character table, we see that it's an infinite group. So you see these dotted lines here in the character table. There's no limit to the number of irreps. And so in this sense, it rather resembles the character table that we see for a spherical atom, for a sphere. And so in the case of a sphere, the irreps were our subshells, S, P, D, F, G, and it just goes on ad infinitum. So not only do these go on ad infinitum, but we also see that the Greek letters that are there are actually the equivalent. So instead of S, P, D, F, we see sigma, pi, delta, phi. And so this hints at a kind of a parallel that we have to the spherical group. And in fact, thinking of it geometrically, the D infinity H group is effectively the operations of a cylinder. It's the symmetry of a cylinder, whereas C infinity V would be a cone. So see, that's with the two ends being different. And likewise, when we look at the different characters, we see one thing that's different between these groups and the spherical group is we see that the looking at the dimensionality of the irreps, the numbers don't just increase and increase. So we see, for example, looking at S, P, D, F subshells, for example, the dimensionality would be going 1, 3, 5, 7, etc. And whereas here we start with 1 on sigma, but then it's just 2 after that. It's just limited to 2. And I think the reason for this is because we only have a single axis in the molecule, which is infinite fold. Then around that axis we're really looking at clockwise or anti-clockwise rotation, and these are the two possibilities. And this is the origin of all those number 2's in the E column, which then begs the question, why is it that the sigma irreps only are one-dimensional? And I think this relates to the fact that for the sigma irreps, this actually doesn't correspond to any rotation at all. And so I think what we see with these Greek letters actually are effectively angular momentum quantum numbers, just like we see with the subshells. And so the sigma irreps, just like we saw with s orbitals, have angular momentum 0, and also, for that matter, 0 angular nodal planes as well. So having angular momentum 0, that's consistent with there being just one state, because there's no sort of clockwise or anti-clockwise way of looking at it, whereas all the other ones, as we have increasing numbers of angular momenta, we look at this increasing amount of angular momentum either clockwise or anti-clockwise, giving these two-dimensional, or these apparently two-dimensional irreps. Now it's quite interesting because when we look at the characters for rotations, and so you see actually around the axis of the molecule we have an infinite number of possible rotation orders, but for rotation for a given angle, phi, let's say, we see 2 cos phi coming out. And in fact that reminds us, doesn't it, of the cyclic groups. And so what we see here actually are that these apparently 2 degenerate states, these, like the cyclic groups, they're actually going to be really representing 2 1-degenerate states just added together. So we saw with the cyclic groups you would have, something like e to the I phi, and as these complex characters, and so we would take plus or minus of the exponent, we'd add them together, and from that we would get the real cos term out. And so we added these 2 complex components to make this apparently doubly degenerate state, although it's not doubly degenerate in the form of being a genuine 2 by 2 matrix. It's really just the sum of 2 1-degenerate states. And so you can see here that as the angular momentum increases, the character of the rotation also increases. So you can see as we go pi delta phi, we have 1, then 2, then 3 in front of the angle there. So the way I'd rationalise the 1, the 2 and the 3 in front of the angle is actually shown in the pictures that we've got in between the 2 tables. So starting off with the pi orbital, this is the second diagram down, we've got 2 p orbitals sideways overlapping to form the pi orbital there. And so you can see in this case, if we wanted to return a character of -1, we would have to do a 180-degree rotation. And so this is consistent with the cos of phi. So if phi is 180 degrees, the cos of phi returns -1, where we've simply switched the phases. Now when you move down to the next diagram, which is the delta bond, so this is the sideways overlap of 2 d orbitals, as is shown. If you wanted to return -1 in this case, you'd only have to rotate 90 degrees to take one lobe on top of an opposite phase lobe. And this is the origin of the 2 phi, because it takes a 90-degree rotation to create this -1 character. And so the 2 phi there, that doubles the 90 to make 180, and so the cos of that returns your -1. So again, if we go to the phi orbital there, this would be the sideways overlap of 2 f orbitals, and so in the case of these f orbitals we're seeing 3 dumbbells. So you notice how we had 1 dumbbell with p, effectively 2 dumbbells with d, now 3 dumbbells with f. So you can see in that particular case, if you want to return the opposite phase, you just need 1/6 of a rotation, and so if you multiply that by 3 phi, that gives you half a rotation, and so the cos of that would then return -1. So that I think makes sense of the 1, 2 and the 3 phis, and these 1, 2 and 3s are the angular momentum. And actually another thing that's worth saying connected to this, as I mentioned before, is the idea of a nodal plane. So you see there, when we've got at the very top diagram there, we've got 2 s orbitals overlapping. Now of course with the s orbitals there's no nodal plane, and so the nodal plane 0 corresponds to angular momentum 0. Then with the p orbitals we've got the 1 nodal plane, angular momentum 1. D orbitals there, we've got 2 nodal planes, angular momentum 2, and with the f orbitals 3 nodal planes, angular momentum 3. And so the more nodal planes you've got, the more the wave function, as it were, goes up and down between positive and negative phase, and so that's the increasing amount of curvature on the wave function. And so actually this all links up to how in fact the angular momentum is defined. So this curvature is mathematically sort of manifest as the second derivative and this is all part of the definition of the angular momentum in quantum mechanics. So next up, if we look at the characters under the C2 rotation, we see these again are going to relate to the atomic orbitals, which is in the sideways overlapping to form these molecular orbitals. And so, for example, in the case of the pi orbital there, or the pi irrep, which relates to the sideways overlap of two p orbitals, of course with a p orbital, if you do a C2 rotation, you simply flip the phases, and so that returns a -1 character, if you like, for each of the sort of doubly degenerate components. But then when you get to the d orbital, you can see there the way those orbitals are built up, 180 degree rotation there. That puts an orbital on top of an orbital of a lobe on top of a lobe of the same phase. So that leads to the +2 character. And then again, when you get to F, you see it works the other way this time. So 180 degree rotation, a positive phase will end up on a negative phase. And so it alternates this positive and negative character as you go along. And so actually this would reflect the parity of the atomic orbital, from which sideways overlap makes the molecular orbital. It's curious in a way that the C2 rotation has a column all to itself, because just next door we've got an infinite number of rotations. I think the reason the C2 rotation is considered separately is because, unlike all the other rotations, it doesn't have like a twin. So you see with the C infinity, it's got a 2 in front of it, and so that's because for every rotation in one direction, you'll have a rotation in the opposite direction, which will have the same character. So you remember, like with a threefold rotation, you could have threefold rotation clockwise or threefold rotation anti-clockwise. But in the case of C2, C2 is kind of standalone. In fact, the C2 would be self-inverse. Now, when it comes to the sigma V planes, these are slightly bizarre. We've got an infinite number of these planes around a cylinder, and how to cope with these? Well, again, when you consider the orbitals as they're shown on the page there, you could have a plane which kind of bisects lobes, and so, well, say if it slices right through lobes on an orbital, then when you do the reflection in that mirror plane, it would just return the same molecular orbital. Whereas if you chose the plane to bisect two lobes, then because all the neighbouring lobes are always opposite phase, it would then return the negative character. And so I think really for all these orbitals where we have nodal planes, the reason you have a 0 character shown in the table is I think it's just really reflecting the average of these positive and negative characters that you can get depending on the orientation of the mirror plane. Of course, a slightly special case is the sigma overlap there, giving you the sigma bond. And so in this case, there are no nodal planes, and so all infinity, if you like, of those sigma V planes will simply return that same orbital, hence the character of 1. So I should say we've got 2 of these sigma irreps. So the sigma plus G, that is the fully symmetric one. So this is what we would associate with the 2 s orbitals, sideways overlapping. And that does beg the question, what is the sigma minus G? So when you look at the sigma minus G, you see that actually has a -1 character for the mirror plane, and also a -1 character for the perpendicular C2 axis. And I think the reason for this, what this represents effectively, is a rotation. It's a bit like a helix. So again, with a helix will be unaffected by rotations around the principal axis, but when you put a mirror in there, that changes it. So a right-handed helix becomes a left-handed helix in a mirror. So the sigma minus G irrep there effectively is the irrep for rotation or a helical shape. So far, the symmetry operations we've considered have been common to the C infinity V and the D infinity H. But it gets more interesting when you look at the right hand side of the D infinity H character table, because now we're seeing the effect of having that perpendicular mirror plane in the middle of the molecule, perpendicular to the principal axis. And so when we look at I now, this is reflection through the centre. Here we see that it makes a big difference now which form of the different orbitals we're looking at. So as you can see there, we've got these in the pictures. We've got the pi, the delta and the phi kind of bonding representation, but of course you can have bonding or anti-bonding orientations. And so actually with the pi g irrep, you can see here that if it's going to be Gerada, that's to say if it's even with respect to reflecting through the centre, then actually it's going to have to be the anti-bonding combination, which is to say that the second p orbital has to be upside down, and this way they reflect into each other through the centre. And so this is why we get the positive 2 there for the character for the I. But on the other hand, when it gets to the delta bond, in this case, because of the parity of the d orbitals, this time the g subscript, delta g, this is going to be the bonding configuration as is shown on the picture there. So that's even with respect to the symmetry reflection through the centre. So you can see there whether the G or the U is bonding or anti-bonding is going to depend on the parity of the atomic orbital, and so that's going to be flipping back and forth as you go along as the parity keeps inverting each time you go down a row in the table. And so you can see there in the bottom half of the table we've got all the ungerada irreps, and so in this case all of the characters for the parity operation have turned negative. I mean, that's the definition of ungerada odd parity there. So whether or not a configuration is bonding or anti-bonding makes a big difference for the improper rotation. So for example with the pi g irrep, because that's an anti-bonding state, then when you do the rotation and then reflect in the perpendicular mirror plane, that's giving you a minus character there, because of course you've got the second p orbital of opposite phase to the first when you have the Gerada symmetry, and then when you go up to the delta, then you don't see that minus sign because the orbital is the other way up for the bonding interaction. And so again we see this alternating positive negative going down the improper rotations. And then when we get to the infinite C2, this is the perpendicular C2 axis, this is rather like we saw with the mirror planes. So depending on how you orient the C2 axis, you can either get a positive or a negative character, and so that 0 there represents an average of the possible orientations of that C2 axis. And so I think it's also quite interesting that on that right hand edge of the character table, when you compare all the characters there with the bottom right hand corner, comparing the G's and the U's, you see that the bottom right is entirely the opposite sign to the top right. And so that's reflecting the fact that you've got this odd and even parity, which is most evident when you've got these reflection operations being used. So the caption there to the left of those pictures just makes it clear how the sigma, pi, delta and phi really make sense as irrep labels, as they represent the orientation from the sideways overlap of the S, P, D and F orbitals. Obviously these are just the kind of Greek translations of the letters. Okay, so this is the point I was making earlier about the numbers in front of the angles representing the angular nodal planes and the angular momentum as illustrated in those pictures. Yes, here's our point about the degeneracy being 2. That's to say we had these positive and negative e to the I phi functions, summing them up to give the real characters, and so that the numbers 2 representing effectively this positive and negative phi effectively representing the clockwise and anti-clockwise rotation that we're considering. And so we've seen in our discussion how the angular momentum, quantum number L, and the parity are affecting the signs of the various characters. And finally we saw C2 as a special case as its self-inverse. Now for the molecular orbital diagram for oxygen. We've seen this before, but actually we're going to be looking at this in a different way now. And so when we look at the sigma and pi labels, in the past we've really come at these simply by kind of physically just pushing the orbitals together and seeing that they can be head on and calling that sigma, sideways on, calling that pi. But what we're going to see now is we can actually arrive at this using our method of making a representation and reducing that representation, and how we're going to see the sigma and pi labels really are actually the irreps, the irreducible representations that we're going to get from reducing our representation of p orbitals. And in fact, one thing I should point out is that, of course, here the sigma and pi labels are lowercase Greek letters, whereas in our character table they were uppercase Greek letters. That's kind of a trivial difference, really. I mean, we tend to use the lowercase letters when we're talking about orbitals and when you're talking about single electron states, and you tend to use the uppercase letters when you're talking about many electron states, but that isn't really a significant difference. So it's rather a neat molecular orbital diagram, the way it shows you the shapes of the orbitals. So we see the familiar p orbitals on the far right and far left, and then in the diagram, in the molecular orbital part in the middle, we see how we've got at the very bottom with the sigma g the head-on overlap, which is in phase, whereas at the very top, sigma u this time, the antibonding, we see the phase mismatch. And the pi orbitals are interesting. So if we look at the lower pi orbitals there, we see that we've got sideways overlap of px in the first case and py in the second case. And then when you move up to the pi star antibonding orbitals, you see this time we've got same sort of geometry, except this time it's a mismatch in the phase. Right, now in terms of actually arriving at this through a representation, what we're going to do is just consider the 6 p orbitals. So 3 p orbitals on each oxygen atom. We're going to take the two together. Of course, we're going to call the internuclear axis the z-axis. We'll call the origin of our system the midway point along the bonds. And one thing that's interesting about this, thinking about the geometry, is that the x and y directions are simply undefined, and so the px and py orbital directions are undefined, because the only direction that is defined in a linear molecule is the axis of the molecule. I mean, how can you say what direction x even is? And so because x and y are both undefined in this way, there's nothing really to distinguish between the two, and so naturally we might expect them to be taken together as some kind of, doubly degenerate type sort of E irrep. And so when it comes to forming a representation, looking at the d infinity h point group, we're going to have to think what to do about these infinities that come up. And so when it comes to the infinite orders of rotation, we're just going to do it for the general angle phi. But when it comes to the mirror planes, this is curious, because what we're going to find is that when you consider px and py together, it doesn't matter what the orientation is of the mirror plane, it always gives you 0 character. So for example, if you consider px and py together, if a mirror plane sliced through the px orbital, for example, then px would return a character of 1, the py would be perpendicular and would be reflected into sort of the opposite phase, and that would give -1. And so they'd cancel to nothing. Likewise, if you had the mirror plane kind of bisecting the px and py orbitals, they'd be reflected into each other, so that would also return a character of 0. And actually this sheds some light on the whole business of mirror planes and the doubled irreps. So you remember before when we were looking at the effect of all the different mirror planes, and we were using our pictorial representation, which just showed a single pi bond to represent the pi irrep. So that meant that we only had one type of a p orbital, say px, for example. And so when there was a single p orbital, then clearly the character would depend on whether the mirror plane was, slicing it in half so that it reflected one lobe into the opposite phase lobe, or slicing both lobes in half, in which case it would return a positive character. But actually, if you think about it, I mean, remember pi, the pi representation is supposed to be this kind of doubly degenerate representation, so we should really be considering px and py together. Now when we were justifying it before, we saw the character table had 2 cos phi in it, and so this reminded us of our cyclic groups, where we were actually summing together 2 complex characters, like an e to the plus I phi and an e to the minus I phi. So when you sum these two together using de Moivre's theorem, it just gives you the entirely real 2 cos phi. And there is actually a connection here, because actually the px and the py orbitals, you can actually derive these from linear combinations of course, the complex functions. So e to the I phi, e to the minus I phi, you sum them together and that basically gives you a px orbital, and you take the difference and it gives you a py orbital. So it's interesting, this kind of doubly degenerate nature of it. We should really be looking at 2 p orbitals at the same time, and that gives us a similar way of looking at it as looking at the positive and the clockwise and the anti-clockwise rotations, which was the other way we looked at it before. And so what we see here now is the character, the representation rather, using the 6 p orbitals. So the character 6, that's obviously just the result of the identity operation. Then the minus 2 there, so this is going to be the effect of doing the C2 rotation. So when we do a C2 rotation, the pz orbitals, which are lying on the axis of the molecule, these are going to be unchanged, so they're going to return a +1 character. But the px and py orbitals on both oxygen atoms, when you give them a 180-degree rotation, they're each going to give a -1 character. So they're going to get 2 +1s and 4 -1s, and that's the origin of the -2 character that we see. Then, then we get the 2 + 4 cos phi. So what's going on here? This is the rotation by phi degrees. So what's happening here is the pz orbitals, they're completely unchanged by the rotation, so they each return a character of 1. So those two together give you the 2. And then the px and the py orbitals on both oxygen atoms, they each return a character of cos phi, so that gives you the 4 cos phi there. This is for the general rotation of any angle phi. Then we've got the this 2 character coming up. The 2 characters from the infinite sigma v planes. So as we explained before, the px and the py orbitals together will always give a character of 0 with these planes, but the pz orbitals will be returned unchanged. So those 2 there come from the 2 pz orbitals. And then the remaining characters of 0, these come from the I operation, the improper rotation s over angle phi, and also the infinite number of C2 perpendicular axes. So all of these operations move essentially the orbitals on one atom to the orbitals on another atom. So these all give a character of 0. So the really neat thing is that if you reduce this representation in the sort of standard way, what you get out of this is exactly the irreps that you see labelling the MO diagram. And so we can arrive at this MO diagram through this much more sort of abstract method of creating a representation and reducing it. And so again, the final point, just to emphasize, is the parity label. So you see that in the case of the sigma bonds, the G label is bonding and the U is anti-bonding. Whereas when you go to the pi orbitals, you see U is bonding and the G is the anti-bonding. So again, if you go to delta orbitals, again it would go back to the G label representing bonding. So that was just something that we mentioned before as well. And now onto the photoelectron spectrum of oxygen. This is very interesting because this really casts a light, really gives you the molecular orbital diagram. It gives you very solid evidence for the molecular orbital diagram. So first, perhaps I should say a little bit about what photoelectron spectroscopy is. So what we do is we irradiate our sample with high frequency light, typically in the ultraviolet. and this is sufficient to ionize our molecule of interest. So a molecule, an electron, will be ejected completely out, so it's taken right up to the ionization limit, the zero of energy, and then it's off into the vacuum, so it's off into freedom, if you like. And so what we would do is we would irradiate the sample with energy, with light of a known frequency and known energy therefore. Then we would look at the kinetic energy of the photoelectrons, the electrons ionized off, and the difference between those two energies must give us the energy that the electron was at in the molecular orbital diagram of our substance. And so I mean, this was famously the work that Einstein got a Nobel Prize for the remarkable discovery that if you increase the intensity of your radiation, you don't get any more kinetic energy off the electrons. And this showed that the whole thing's quantized, that light's quantized, the electrons are quantized. So if you use a greater intensity of light, there's just more photons coming in, so you just get more photoelectrons coming off, but of the same energy. And the energy of the photoelectrons only depends on the frequency of the light. So obviously if the frequency of the light isn't quite as, the energy it corresponds to isn't quite as great as the ionization energy, you'll never get any photoelectrons off, regardless of the intensity. And so one thing that's interesting about this is that we can read off the spectrum straight away the ionization energy. So we see the photoelectron spectrum of dioxygen there, and you can see there on the x-axis, if we go to the far right there, which has the smallest energy, we see a peak at just over 12 electron volts. And so then this is the minimum amount of energy to remove an electron. So it's like how we define the ionization energy. And what's interesting about this is that the ionization energy of the O2 molecule is less than the ionization energy of an oxygen atom. And so this really goes to show then that the electron that you're ionizing in an oxygen molecule must be an antibonding electron. That's to say, it must have a higher energy than the non-bonding state in the atom. And so one point to emphasize from the molecular orbital diagram that we saw on the previous slide, we were just considering the 2p subshell. So of course oxygen being group 16 or group 6, it's got 6 electrons in its outer shell, 2 of them are in the s subshell, leaving 4 in the p subshell. And so the 4 p electrons from each oxygen atom come together to feed 8 electrons into our molecular orbital diagram. And so they go in pairs. So the bottom pair will go in the sigma bond, then the next 2 pairs will go into the pi bond, and so that's 6 electrons taken into account. Then the last 2 electrons have to go up into the pi star level, but there you've got 2 degenerate orbitals in the pi star level and 2 electrons to go in. And so the electrons choose to go in separate orbitals to keep apart from each other. And so this actually is going to give us all our really interesting properties of oxygen. First up, the fact that the highest energy electrons are in antibonding orbitals, first of all, gives us this surprisingly low ionization energy of the oxygen molecule. And then the other interesting thing that comes out is all this structure in the spectrum. But first of all, I mean, if we take a general look at the spectrum, you can say that between 12 and 13 electron volts, this basic band in the spectrum represents ionizing the electrons in the pi star level. But of course, as the energy gets cranked up, we can also start ionizing electrons in lower levels. So the next kind of group of peaks, that general band there, the next one along, say between 16 and 18 electron volts, that will represent ionization of electrons from the next level down, which would be the pi bond. And then the peaks between 18 and 19 electron volts, that will correspond to ionizing electrons from the sigma bond underneath that. So in that sense, the photoelectron spectrum really gives us the energy levels in the molecular orbital diagram. So it's good evidence that our molecular orbital diagram is, physically reasonable. And then of course this then leads us to all these multiple peaks that make up these different bands, and can we explain what's going on there? And so this is an interesting phenomenon where as we remove an electron from the molecule, we're removing electrons from either bonding or anti-bonding orbitals, and this is going to affect the bond order of the molecule. So in our molecular orbital diagram, we've got 3 bonding orbitals that are occupied with electrons. So that looks like it's a triple bond. But then our final 2 electrons are in anti-bonding orbitals. So that's the equivalent of an antibond. So actually 3 bonds and 1 antibond would combine to give you our bond order of 2. So in the case of oxygen, when we ionize, say within about 12 electron volts, we remove an electron from an anti-bonding orbital. So the bizarre thing that results from this is that the ionized form of the oxygen atom, O2 1+, actually has a stronger bond because we remove one of the anti-bonding electrons. So actually the bond order goes up from 2 to 2.5. This is a bit weird. I mean, you wouldn't normally consider a sort of ionized species to have a more stable bond, but it would. But what's interesting about this is that you see the ionization process is going to be very fast. The electron will be kind of whipped out of the molecule so quickly that the nuclei, which are much sort of slower and heavier in comparison, wouldn't have had time to move. And so when that electron gets whipped out of the molecule, the resulting ion has this increased bond order of 2.5. And because it's got an increased bond order, what we normally expect to see with a stronger bond is a shorter bond. So the equilibrium distance between the 2 nuclei in the O2 1+ ion will actually be shorter than it would be in the normal oxygen molecule. So in the instant that we create the O2 1+ ion, actually the nuclei are too far apart. The bond is stretched compared to its equilibrium distance. And so what we're doing is, as the nuclei move together to try and correct for this, they actually create a vibration in the bond. And so in sort of changing the bond order by ionizing the molecule, we actually set up a vibrationally excited ion that's formed. And similarly, if you ionize an electron from a pi bonding orbital or a sigma bonding orbital, then what you're doing then is by removing an electron from a bonding orbital, you're lowering the bond order of the molecule, so the oxygen would go down from bond order 2 to bond order 1.5, and then we get a similar argument working the other way. And so then the equilibrium bond distance would actually be a bit longer in the ion than it would be in the molecule. And so the atoms try and correct for this, and again they set up a vibration. So we set up these vibrations, and so what we see then in all these little peaks associated with each band is effectively a vibrational spectrum on top of an electronic spectrum. So we're doing electron excitation but setting up vibrational excitations at the same time. And so this is called vibronic. So it's like electronic and vibrational combined. And just a little bit about units. So I mean, kilojoules per mole would be a unit that chemists use a lot for energy, molar energy. When we do infrared spectroscopy, often those spectra are given in centimeters to the -1. So it's an inverse wavelength, or a wave number, the number of waves in a certain distance. And so the wave number is proportional to energy. Obviously it's not the same thing as an energy. And in this spectrum we've got units of electron volt. So of course a volt is a joule per coulomb, and then you multiply that by the number of coulombs in the electron charge and you get the electron volt. So 1 electron volt will be 1.6 times 10 to the -19 joules. And so this is for like an individual an individual atom or an individual electron being ionized. And so here we've got 2 expressions for energy. So it could be the charge times the voltage, like we see here with the electron volts. And if you're going to be working in wave numbers, then we have this other expression, E equals hc, and then it's nu bar. That's a Greek letter nu, and nu bar represents the wave number, the number of waves per unit length. And because wave number is given in per centimetre, it does mean actually that in this context, c, the speed of light, would need to be given in centimetres per second for this all to ultimately work out in joules. H there is Planck's constant. So there you go. There's a lovely piece of experimental evidence there through the photoelectron spectrum, which kind of adds weight to our molecular orbital picture. The one thing we can't yet explain are some of the other strange properties of oxygen. The fact that liquid oxygen is blue, and also if you can generate singlet oxygen in a chemical reaction, that actually luminesces red. And these are both kind of bizarre, strange things that to explain them we need to go into a little bit more detail with our understanding of the electron structure of oxygen. So the one thing we've not really looked at yet is actually what happens in that pi star, those pi star orbitals. So they're rather special because normally in molecules we see the electrons being fully paired up. And so, like I mentioned before with the methane example, was with all the electrons paired up in orbitals, all the angular momentum cancels out. But oxygen's special because it's got these two unpaired electrons in the pi star level. And so being unpaired, those electrons are magnetic because they have charge and spin that's not cancelled out. So this leads to the magnetism that's seen in oxygen. And the other thing that we're going to see is that because they're unpaired, they're going to interact with each other in some quite interesting ways. And we need to look at that interaction in detail if we're to understand these colours blue and red that get associated with oxygen. So we'll look at that next time.